This is the finale. 45 episodes ago, we started a journey by asking what it meant for a function f of x to approach a value, and we built a limit out of epsilons and deltas. Out of that single definition came the derivative, the integral, the fundamental theorem of calculus, Taylor series, partial derivatives, gradients, multiple integrals, line integrals, the fundamental theorem of line integrals, and last episode, Green's theorem. And here's what I want you to see today. Those last few results are not a grab bag of unrelated identities. They are the same theorem, applied at different dimensions, with different objects playing the role of derivative and boundary. The unifying statement is one line of differential form notation, the integral over the boundary of m of omega equals the integral over m of d omega. The integral of a form over the boundary equals the integral of its derivative over the interior. Today we climb into 3 dimensions, meet Stokes' theorem for surfaces and the divergence theorem for solids, and then assemble the whole picture. By the end, you will see the fundamental theorem of calculus, the fundamental theorem of line integrals, Green's, Stokes', and divergence as 5 faces of the same identity. Welcome to the finale. Look at the stack. At the top is the fundamental theorem of calculus from episode 22 of this series. An interval, a to b. The integral of f prime of x over the interval equals f of b minus f of a, the value of f evaluated on the boundary of the interval, which is just the 2 endpoints. Already the pattern is there. Integrate a derivative over a region. Evaluate the antiderivative on the boundary. Below it, the fundamental theorem of line integrals from 2 episodes ago. A curve C from a to b. The integral of the gradient of f along the curve equals f of b minus f of a. The boundary of a curve is its 2 endpoints. We evaluate f there. Below that, Green's theorem from last episode. A planar region D with boundary curve C. The boundary integral of f equals the double integral of the curl over D. Now we add 2 more layers. A surface in 3 dimensions, S with a boundary curve, the boundary of S. Stokes' theorem says the line integral of S around the boundary of S equals the flux of its curl through S. And a solid region V with closed boundary surface, the boundary of V. The divergence theorem says the flux through the boundary equals the integral of divergence over the solid. 5 theorems, 1 slogan. Boundary integral equals interior integral of a derivative. The dimension goes up, the structure is the same. That is the architecture of calculus. Before stating Stokes' theorem, we need the 3-dimensional curl. For a vector field, f the vector p, q, r on 3-dimensional space, the curl is the vector del cross f, whose components are r sub y minus q sub z, then p sub z minus r sub x, then q sub x minus p sub y. A clean way to remember it is the symbolic determinant. The top row is I, j, k, the middle row is the partial derivative operators, the bottom row is p, q, r, and you expand by cofactors as you would any 3x3 determinant. Notice the pattern. Each component is a difference of mixed partials with a cyclic permutation of the variables. The physical meaning is the same as in 2 dimensions, upgraded. At a point, del cross f is itself a vector. Its direction is the axis of local rotation, the direction in which a tiny paddle wheel would spin most rapidly, and its magnitude is twice the angular speed. You can think of curl as circulation density per unit area, oriented along the axis of spin by the right-hand rule. Quick sanity check, take f to be a 2-dimensional field embedded in 3 dimensions, with r equals 0 and p, q independent of z. The curl collapses to the vector 0, 0, q sub x minus p sub y, a vector pointing purely in the k direction whose length is the 2-dimensional curl from last episode. So the 2-dimensional curl was the out-of-page component of the 3-dimensional curl all along. Here is Stokes' theorem. Let S be a piecewise smooth-oriented surface in 3-dimensional space. You can picture a hemisphere or a soap film stretched across a wire loop. The surface has a boundary, which is a closed curve we call the boundary of S. Read the boundary of S. The orientations have to be compatible via the right-hand rule, which we will unpack on the next slide. For a continuously differentiable vector field f, Stokes' theorem says the line integral of f around the boundary of S equals the surface integral of the curl of f through S circulation around the rim equals flux of curl through the cap. Stare at that. The left-hand side lives on a 1-dimensional curve. The right-hand side lives on a 2-dimensional surface. They are equal. Even more strikingly, the right-hand side appears to depend on S, but the left-hand side depends only on the boundary of S. So if 2 different surfaces, S1 and S2, have the same boundary curve, they give the same flux of curl. You can swap the hemisphere for the flat disk it caps, the flux of curl is unchanged. That independence is one of the most useful computational consequences of Stokes'. Pick the easiest surface bounded by your curve. Now the orientation convention, because otherwise the signs make no sense. A surface in 3 dimensions has 2 unit normal directions, and picking one orients the surface. Once you have picked n, the boundary curve gets a compatible orientation by the right-hand rule. Here it is in concrete terms. Point the thumb of your right hand in the direction of n. Your fingers curl in the direction the boundary of S should be traversed. An equivalent statement: walk along the boundary of S in the direction of orientation with your head pointing in the n direction. Then the surface S is on your left. This is exactly the same interior on the left rule we used for Green's theorem, lifted into 3 dimensions. For example, take the upper hemisphere of the unit sphere with n pointing outward and upward. The boundary is the unit circle in the xy plane. The right-hand rule says the boundary of S is the unit circle traversed counterclockwise as seen from above, exactly the conventional positive orientation in the plane. Reverse the normal, you reverse the boundary, and both sides of Stokes' theorem flip sign together. The identity stays true, only the bookkeeping flips. This is the 3-dimensional shadow of the 2-dimensional orientation rule. Now we can compute. Before we do examples, let me show you why Stokes' theorem deserves the title 3-dimensional generalization of Green's. Specialize S to be a flat planar region D sitting in the xy plane, oriented upward so n equals k. The surface area element ds is the ordinary planar area element dA, so nds is just k, dA. Take a 2-dimensional vector field, f the vector p, q, 0, with p and q independent of z. The curl is del cross f equals the vector 0, 0, q sub x minus p sub y as we computed 2 slides ago. Dotted with k, we get q sub x minus p sub y exactly. Plug into Stokes' theorem, the left side is the closed line integral over the boundary of d of f dot dr. The right side is the double integral over d of q sub x minus p sub y dA. That is Green's theorem, letter for letter. The boundary orientation is counterclockwise because the right-hand rule with thumb up gives counterclockwise fingers. Everything matches. Green's theorem is Stokes' theorem applied to a flat surface in the plane. Stokes' theorem is Green's theorem freed from the plane, free to drape over hemispheres, soap films, and any oriented surface you like. First worked example, verifying Stokes' on a familiar field. Take f the vector negative y, x, 0, the rotational field we have been computing with since episode 12. Let S be the upper unit hemisphere with the upward-outward pointing normal. The boundary of S is the unit circle in the xy plane. By the right-hand rule with n upward, the boundary of S is traversed counterclockwise as seen from above. First, compute the curl. The components of f are p equals negative y, q equals x, r equals 0. So r sub y is 0, q sub z is 0, first component is 0, p sub z is 0, r sub x is 0, second component is 0, q sub x is 1, p sub y is negative 1, third component is 1 minus negative 1 equals 2. The curl is 2k, a constant vector field pointing straight up. Now the line integral. Parametrize the unit circle, x equals cosine t, y equals sine t, t from 0 to 2 pi. The integrand is negative y dx plus x dy equals negative sine t times negative sine t dt plus cosine t times cosine t dt equals sine squared t plus cosine squared t dt equals dt. Integrate from 0 to 2 pi, result is 2 pi. Now the surface integral, and here we use a beautiful Stokes' trick. The right-hand side depends only on the boundary. We are free to replace the hemisphere by any surface with the same boundary. The easiest one is the flat unit disk D in the xy plane. There n equals k, so 2k dotted with n is 2. The surface integral becomes the double integral over d of 2, dA, which is 2 times the area of the unit disk equals 2 times pi equals 2 pi. Both sides agree, 2 pi equals 2 pi. Stokes' theorem verified. The other star of the show is divergence. For a vector field, f the vector p, q, r, on 3-dimensional space, the divergence is the scalar del dot f equals p sub x plus q sub y plus r sub z. It is the sum of the diagonal partial derivatives, the trace of the Jacobian, if you like the linear algebra angle. The physical meaning is sharper than curl. At a point, del dot f is the net outflow of f per unit volume. If you imagine f as the velocity field of a fluid, then at a point where divergence is positive, the fluid is being created, a source. Where divergence is negative, fluid is being destroyed, a sink. Where divergence is 0, fluid is just flowing through, incompressibly. Quick examples. The radial field, f the vector xyz, points outward from the origin and its divergence is 1 plus 1 plus 1 equals 3 everywhere. Uniform source density. The rotational field f the vector negative y, x0, has divergence, 0, pure rotation, no sources. The inverse square field of a point charge has divergence 0 everywhere except at the origin, where all the divergence is concentrated, a Dirac delta source. These 3 examples cover almost every situation you will ever meet in physics: uniform expansion, rotation, and isolated charges. Here is the divergence theorem. Let V be a solid region in 3 space, a ball, a cube, a coffee mug. With a piecewise smooth closed boundary surface, the boundary of V oriented with outward unit normal n. For a continuously differentiable vector field f, the surface integral of f dot n over the closed boundary, the boundary of v, equals the triple integral of del dot f over the solid v. Total flux out through the boundary equals the total divergence content inside. A two-dimensional integral on the left, a three-dimensional integral on the right. The same dimension jump as in Green's and Stokes's. The surface integral on the left is over a closed surface. In some textbooks, this is written with a small circle through the integral sign. The intuition is conservation of stuff. Picture f as the velocity of an incompressible fluid carrying some conserved quantity, charge, mass, heat. The divergence at a point is the rate of creation per unit volume. The flux through a closed surface is the rate at which the quantity is leaving the region enclosed. Conservation says total creation inside equals total outflow through the boundary. That is the divergence theorem in plain English. For an incompressible flow where del dot f equals 0 everywhere, the net flux through any closed surface is 0. Whatever flows in must flow out. The flux form of Green's theorem from last episode is the two-dimensional shadow of this. Second worked example, the cleanest possible illustration of the divergence theorem. Let V be the closed unit ball and the boundary of V the unit sphere, oriented outward. Take F the vector x, y, z, the radial position field. The divergence is del dot f equals 1 plus 1 plus 1 equals 3, constant. The triple integral side is the triple integral over V of 3, dv, which is 3 times the volume of the unit ball. Volume of the unit ball is 4/3 pi, so 3 times 4/3 pi equals 4 pi. Now the direct flux check, the satisfying sanity test. On the unit sphere, the position vector, the vector xyz, has length 1 and points radially outward, so it is the outward unit normal. That makes f dot n equal to f dot f over the magnitude of f, which is x squared plus y squared plus z squared equals 1. The flux integrand is identically 1 on the sphere, so the flux is just the surface area of the unit sphere, which is 4 pi. Both sides agree, 4 pi equals 4 pi. The divergence theorem converted a surface integral over a curved sphere into a trivial constant times a volume. That is the kind of simplification that makes the theorem indispensable in physics. Gauss's law for electric and gravitational fields is literally this identity applied to the appropriate inverse square law. Third worked example, smaller but more instructive because it shows how the divergence theorem replaces 6 surface integrals over the faces of a cube with one triple integral. Take V, the unit cube, the unit interval cubed, and the strange little field f the vector x squared y, 0, 0. Only one component is non-zero, and it depends on x and y but not z. The divergence is the partial with respect to x of x squared y, which is 2xy plus 0 plus 0. So del dot f equals 2xy. Set up the triple integral, the integral from 0 to 1, of the integral from 0 to 1, of the integral from 0 to 1 of 2xy dz dy dx. The integrand has no z dependence, so the z integral contributes a factor of 1. We are left with the integral from 0 to 1 of the integral from 0 to 1 of 2xy dy dx. The inner y integral is x times y squared, evaluated from 0 to 1, giving x. The outer x integral is the integral from 0 to 1 of x dx equals 1/2. Triple integral side 1/2. Now the direct flux check, which is genuinely instructive. The cube has 6 faces. On 5 of them, f has no normal component or is 0. The face x equals 0, f equals the vector 0 times y, 0, 0, which is the 0 vector, no contribution. The faces y equals 0, y equals 1, z equals 0, z equals 1, the outward normal is plus or minus j or plus or minus k, but f has no j or k component, so f dot n equals 0, no contribution. The only face that contributes is x equals 1, where f equals the vector y, 0, 0, and n equals I, so f dot n equals y. The flux through that face is the integral from 0 to 1, of the integral from 0 to 1, of y dy dz equals 1/2 times 1 equals 1/2. Both sides give 1/2. The divergence theorem has condensed 5 vanishings and 1 phase computation into a tidy triple integral. Now the punchline of the whole course. Mathematicians, especially Ailé Cartan in the early 20th century, asked, what is the common structure behind the fundamental theorem of calculus, the fundamental theorem of line integrals, Green's, Stokes's, and divergence? The answer is the language of differential forms. A k-form omega on a manifold M is the kind of object you integrate over a k-dimensional region. A 0 form is a function, you integrate it by evaluating at points. A 1 form is what lives under a line integral, p dx plus q dy is a 1 form. A 2 form is what lives under a surface integral. A 3 form is what lives under a volume integral. Each form has an exterior derivative, d omega, which raises its degree by 1 and generalizes the gradient, curl, and divergence simultaneously. And every k-dimensional region M has a k-1 dimensional boundary, the boundary of M. With all that machinery, here is the master theorem. Due to Eli Cartan, the integral over the boundary of m of omega equals the integral over m of d omega. One line. The integral of omega over the boundary of m equals the integral of its exterior derivative over m. Read at dimension 1, with m the interval a to b and omega equals fa0 form, it is the fundamental theorem of calculus. With m a curve in space, the fundamental theorem of line integrals. With m a planar region, Green's. With m a surface in 3 space, Stokes's. With m a solid, Divergence. 5 theorems we have spent 5 episodes on, packed into one tidy line. This is what the rest of mathematics calls the fundamental theorem of calculus, the generalized Stokes' theorem. A brief history of the theorems carrying these names. The divergence theorem was used implicitly by Gauss in his 1813 work on gravitation, and was rigorously proven in full generality by the Russian mathematician Mikhail Ostrogradsky in St. Petersburg in 1826, before Green's 1828 essay. In Russia, the divergence theorem is still routinely called the Ostrogradsky theorem, and he deserves the credit. Stokes' theorem has the most amusing origin story. The curl identity on surfaces was written down by William Thomson, the future Lord Kelvin, in a letter to George Gabriel Stokes in July 1850. Stokes was the Lucasian professor of mathematics at Cambridge, Newton's old chair, currently held by Stephen Hawking's successor. 4 years later, in 1854, Stokes set the Smith's Prize exam at Cambridge, the toughest mathematics competition for graduating students of the era, and included as a problem, "Prove this identity that Kelvin sent me." The name stuck. Stokes did not discover the theorem, he gave it as a Cambridge exam problem. That is how mathematical history sometimes works. Finally, the unification under differential forms is due to the French geometer Eli Cartan in the early 20th century. The modern packaging of all 5 theorems as the integral over the boundary of m of omega equals the integral over m of d omega is his invention. And the cohomology theory built on that observation by Georges de Rham in 1931 is one of the foundations of modern topology, the bridge where calculus walks into algebraic topology and never comes back. Recap. Stokes' theorem says that for an oriented piecewise smooth surface S in 3-dimensional space with boundary, the boundary of S, oriented compatibly by the right-hand rule, the line integral of f around the boundary of S equals the flux of del cross f through S. Circulation equals flux of curl. The divergence theorem says that for a solid V with closed outward-oriented boundary surface, the boundary of V, the flux of f through the boundary of V equals the triple integral of del dot f over V. The 3-dimensional curl is the vector r sub y minus q sub z, p sub z minus r sub x, q sub x minus p sub y, measuring local rotation direction and rate. The 3-dimensional divergence is the scalar p sub x plus q sub y plus r sub z, measuring local source strength. Orientation is set by the right-hand rule, thumb along n, fingers curl along the boundary of S. We verified Stokes's on the upper unit hemisphere with f the vector negative y x0, both sides equal 2 pi. We verified the divergence theorem on the unit sphere with f the vector x, y, z, both sides equal 4 pi. We did one more example on the unit cube with f the vector x squared y, 0, 0, both sides equal 1/2. And finally, the big picture, the fundamental theorem of calculus, the fundamental theorem of line integrals, Green's, Stokes, and the divergence theorem are all instances of the generalized Stokes theorem on differential forms. The integral over the boundary of m of omega equals the integral over m of d omega. One idea, 5 faces. One more slide. I want you to step back and see the whole road. Episodes 1 through 15 were differential calculus, we built the limit, the derivative, the rules, implicit differentiation, the mean value theorem, Taylor series. Episodes 16 through 30 were integral calculus, Riemann sums, the fundamental theorem, substitution, integration by parts, partial fractions, improper integrals, infinite series. Episodes 31 through 45, this multivariable series, took the derivative and the integral and lifted them into 2 and 3 and arbitrarily many dimensions. Partial derivatives, gradients, directional derivatives, Lagrange multipliers, multiple integrals in every coordinate system, line integrals, the fundamental theorem of line integrals, Green's, and today Stokes's and divergence. 45 episodes, 3 semesters of university calculus, something like 15 hours of video. What is the takeaway? Calculus is not a pile of tricks. It is one idea, d, the exterior derivative, differentiation. And the fundamental theorem comes in dimensions 1, 2, and 3 with different names. The fundamental theorem of calculus, Green's, Stokes, divergence. They are all the integral over the boundary of m of omega equals the integral over m of d omega. We started with epsilon and delta. We end with d. That is the architecture of calculus, and that is what I hoped you would see by the end. If you stuck with me through all 45 episodes, thank you. You have earned it. And that is the playlist. Stokes' theorem and the divergence theorem in 3 dimensions, the unification of all 5 fundamental theorems of calculus under differential forms, and the close of a 45-episode journey. Where to next? If this course has whetted your appetite, the natural follow-ups are real analysis, which goes back to the limit and proves everything rigorously, differential geometry, which is calculus on curved spaces and where Stokes' theorem really lives, or partial differential equations, complex analysis, or topology, all of which use the tools we have built. Or, and this is my favorite suggestion, loop back to episode 1, What is a Limit, and watch it again with everything you now know. The epsilons and deltas will hit differently. A final challenge for the road: use the divergence theorem to compute the flux of f the vector x cubed, y cubed, z cubed outward through the unit sphere. The divergence is 3 times x squared plus y squared plus z squared, convert to spherical coordinates, integrate, you get 12 pi over 5, boundary equals interior. 1 idea, 5 faces, 3 semesters, 15 hours, 1 playlist. Thank you for watching. Now go and use it. Stokes' theorem. For an oriented piecewise smooth surface S in R cubed with boundary curve partial S oriented compatibly by the right-hand rule, and a C to the 1 vector field F, oint partial SF dot doctor equals I and S of del cross F dot N ds. Circulation around the rim equals flux of curl through the cap. Divergence. Gauss theorem. For a solid region V subset R cubed with closed outward oriented boundary partial V, I and partial Vf dot n ds equals I and B del dot F dV. Flux through the boundary equals total divergence inside. The 3D curl is del cross F equals the vector Ry minus Qz, Pz minus Rx, Qx minus Py, and the divergence is del dot F equals Px plus Qy plus Rz. Worked examples: Stokes is verified for F equals the vector minus y x0 on the upper unit hemisphere, both sides equals 2 pi, divergence theorem on F equals the vector xy, z through the unit sphere, both sides equals 4 pi, and F equals the vector x squared, zeros to the unit cube, both sides equals 1, 2, 2. Green's theorem is Stokes's on a flat surface. The divergence theorem is the 3D flux version. All 5 fundamental theorems of calculus, FTC, FTLI, Green's, classical Stokes's, and divergence, are instances of the generalized Stokes' theorem in T partial m omega equals in T m d omega on differential forms due to Cartan. The course ends with the realization that calculus has one big idea, repeated at every dimension. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.